You're wrong about light. I don't mean that as an insult. I mean every single human being who ever lived before 1905 was wrong about light. The greatest physicists in history, people with names like Newton and Maxwell, brilliant minds who could predict the motion of planets and unravel the secrets of electricity, they were all missing something fundamental, something so basic, so essential, that once you see it, the entire universe transforms before your eyes. And here's the wildest part. A 6-year-old kid figured out what they were all missing, not in a laboratory, not with fancy equipment, just by asking one simple question while daydreaming during a boring afternoon. That kid was Albert Einstein. And the question he asked, what would I see if I chased after a beam of light? Now, you might be thinking, okay, that's a weird question, but what's the big deal? Kids ask weird questions all the time. But this question broke physics, shattered it completely. Because when Einstein really thought it through, when he pushed his imagination to follow that light beam, he discovered something that should be impossible. Something that makes no sense according to everything we think we know about how the universe works. And yet it's true. See, light doesn't obey the rules. It doesn't work like anything else in the universe. You can't catch up to it. You can't slow it down from your perspective. You can't race alongside it and watch it freeze. And when physicists finally accepted this, when they really internalized what this meant, everything changed. Time became flexible. Space became stretchy. The idea of now became meaningless. The universe revealed itself to be far stranger, far more beautiful, and far more shocking than anyone had imagined. Today, I want to take you on the same journey Einstein took. I want to show you what he saw when he was just a teenager, sitting there imagining riding alongside a light beam. Because once you see it, once you really understand what light is doing, you can't unsee it. Your intuition about reality will never be the same. We're going to start with something simple, throwing a ball on a train. Then we'll move to something weirder, trying to catch up to light. And by the end of this video, you're going to understand why time slows down, why space contracts, why there's no such thing as absolute simultaneity, and why Einstein's discovery is the most mind-bending revelation in the history of physics. But here's what I want you to remember throughout this journey. Einstein didn't need a laboratory. He didn't need billion-dollar particle accelerators or advanced mathematics. He just needed imagination, the willingness to ask what if, and follow the logic wherever it led, even if it seemed impossible. Especially if it seemed impossible, because that's where the truth was hiding, in the impossible. So buckle up. We're about to chase a light beam, and when we catch up to it, or rather, when we discover why we can't catch up to it, everything you think you know about reality is going to flip upside down. Let's go. Okay, let's start with something that makes perfect sense, something your brain has no problem with at all. Imagine you're on a train. The train is moving forward at, let's say, 60 miles per hour. You're standing in the aisle, and you throw a ball forward at 20 miles per hour relative to you, relative to the train. Now, here's the question. How fast is the ball moving relative to someone standing on the platform outside watching the train go by? Easy, right? 80 miles per hour. You just add them up. The train is going 60. The ball is going 20 more in the same direction. So to the person on the platform, that ball is zipping along at 80 miles per hour. Simple addition. This is how velocities work. This is how the universe works. Or let's flip it. Say you throw the ball backward at 20 miles per hour. Now, how fast is it moving relative to the platform? And 40 miles per hour, right? You subtract the train's speed minus the ball's speed, gives you 40 miles per hour moving forward. This makes perfect intuitive sense. It's how we experience the world every day. Speeds add, speeds subtract. Motion is relative to your frame of reference, but you can always add and subtract velocities to figure out what something looks like from a different perspective. Newton's laws, classical mechanics, everything we learned in physics class, it all says this is how the universe works. Velocities add together. Always. No exceptions. Now, let's talk about light. You're on that same train, still going 60 miles per hour. But this time, instead of throwing a ball, you turn on a flashlight. The light beam shoots forward at, well, the speed of light. Let's call it 186,000 miles per second, because that's what it is. So here's the question. How fast is that light beam moving relative to someone standing on the platform? Your brain immediately said, easy, same as before. The train is moving forward, the light is moving forward, so you add them up. The light should be moving at 186,000 miles per second plus, whatever the train speed is. Right? Wrong? Dead wrong? Here's what actually happens, and this is where physics breaks. The person on the platform measures the light moving at exactly 186,000 miles per second, not a single mile per second faster. The exact same speed. Wait, what? That's impossible. That breaks the rules of addition. Yes, it does. And that's the point. Now let's make it even weirder. You turn around and shine the flashlight backward toward the rear of the train. The light is going the opposite direction of the train's motion. Your brain says, okay, so now we subtract. The light should be moving slower relative to the platform. Nope. The person on the platform measures the light at exactly 186,000 miles per second. Same speed, always the same speed. You could speed up the train, slow down the train, point the flashlight forward, backward, sideways, doesn't matter. Every single observer, no matter how fast they're moving, no matter what direction they're going, measures light at exactly the same speed. This is what experiments showed. This is what reality kept screaming at physicists in the late 1800s. Light didn't care about your motion. It didn't care about reference frames. It just went at one speed, the speed of light, and that speed was absolute. This made no sense. This violated everything physics said should be true. Velocities should add. That's fundamental. That's basic. That's how motion works. But light said, nope, I don't care about your rules. Now, physicists tried to explain this. Oh boy, did they try. They invented something called the luminiferous ether, this invisible substance that filled all of space, and light was supposedly a wave in this ether, like sound waves in air. They thought maybe light always moves at the same speed relative to the ether, and that's why the measurements came out weird. But then experiments showed there is no ether. The famous Michelson-Morley experiment in 1887 searched for it and found nothing. Absolutely nothing. Space is empty. Light just moves. At one speed, always, physicists were stuck. Completely stuck. They had experimental results they couldn't explain with any theory that made sense. And this is where one 6-year-old Einstein enters the picture. So imagine you're Einstein. You're 16 years old. It's 1,895. You're not in some prestigious university. You're just a teenager. Kind of a troublemaker, actually. Not particularly great at following the rules. And one day, you're thinking about light. Because that's what you do. You think about physics. And you ask yourself this question. What would a light wave look like if I chased after it, running at the speed of light? Now, this is a thought experiment, pure imagination. Einstein pictures himself somehow moving at the speed of light. Maybe he's on a motorcycle. Maybe he's just flying through space. Doesn't matter. And he's catching up to a light wave. He's matching its speed. He's right there beside it. And he asks, what do I see? According to everything physics knew in 1895, the answer seemed obvious. If you're moving at the same speed as the light wave, then relative to you, the light wave should appear frozen. Stationary. Just sitting there in space like a frozen electromagnetic field. Think about it like ocean waves. If you're standing on the beach, waves come rolling in, one after another. But if you're a surfer paddling at the exact same speed as a wave, That wave appears frozen relative to you. You're riding it. You're moving with it. It's not moving past you anymore. So light should be the same, right? If you match its speed, it should appear frozen. And this is where Einstein's brilliant teenage brain said, wait a minute, that's impossible. Here's why. Light is an electromagnetic wave. It's oscillating electric and magnetic fields, each one creating the other, propagating through space. Maxwell had figured this out a few decades earlier. The equations were beautiful. They showed that light is a self-sustaining wave of electromagnetism. But, and here's the crucial part, those equations, Maxwell's equations, don't allow for a frozen electromagnetic wave. They don't permit a stationary pattern of electric and magnetic fields just sitting there in space, not moving, not changing. A frozen light wave is a contradiction. It violates the very equations that describe what light is. Let me put it another way. Imagine you could somehow freeze time and look at a light wave. What you'd see is an electric field pointing one direction, creating a magnetic field pointing perpendicular to it, and that magnetic field changing in a way that creates a new electric field, and round, the wave exists because these fields are in motion, creating each other, propagating. If you freeze it, if you move alongside it, so it appears stationary relative to you, it's not a wave anymore. It's just static fields sitting there. And static fields like that don't create each other. They don't propagate. They don't exist. Not according to Maxwell's equations. So Einstein, at age 16, realized he found a paradox, a genuine physics-breaking paradox. If you could travel at the speed of light, you should see a frozen light wave. But frozen light waves can't exist. They're forbidden by the equations that describe light. So, what gives? Most people, when they hit a paradox like this, would just shrug and move on. It's probably nothing. Maybe I'm thinking about it wrong. But Einstein wasn't most people. Einstein was the kind of person who, when he found a contradiction in physics, assumed the contradiction was telling him something profound. That reality was trying to reveal a secret. He sat with this paradox. He thought about it for years. It haunted him. This frozen light wave that couldn't exist. And eventually, he realized something revolutionary. Maybe the problem isn't with the light wave. Maybe the problem is with the entire premise of the question. Maybe you can travel at the speed of light, not because it's technologically impossible, not because we haven't built a fast enough rocket, but because the universe itself forbids it. Because the speed of light isn't just fast, it's fundamental. It's the speed limit of causality. Nothing with mass can reach it. Nothing can catch up to light. But why? Why would the universe have this rule? And this is where Einstein made his leap. This is where he saw what no one else could see. He realized, what if light doesn't just move at one speed? What if light must move at one speed relative to everyone, no matter how fast they're moving? What if the speed of light is absolute? Now, your brain immediately rebels against this. That's impossible. That violates how velocities add. Yes, it does. Which means something's wrong with our understanding of how velocities add. Something's wrong with our understanding of space and time. Because think about it. If light is always moving at the same speed relative to you, no matter how fast you're moving, then when you try to chase after it, when you try to catch up, you can't. You can run toward it, you can accelerate to tremendous speeds, but that light is still moving away from you at the exact same speed it was before you started running. It's like chasing the horizon. You can run toward it, but it always stays the same distance away. This means the frozen light wave Einstein imagined, it doesn't exist because you can't create the conditions for it to exist. You can never catch up. You can never match light's speed. The universe won't let you. But here's the problem, and oh boy is this a problem, if the speed of light is absolute, if it's the same for everyone, no matter how fast they're moving, then something else has to give. Because velocity should add, that's basic math. Basic logic. Unless, unless space and time themselves are flexible. Okay, this is where we get to the absolute core of Einstein's revelation, the thing that changes everything. Einstein realized that the only way for the speed of light to be the same for everyone, for every observer, no matter how fast they're moving, is if space and time are not fixed, they're not absolute. They're not the same for everyone. They're relative. Let me show you what this means with one of the most famous thought experiments in physics. Imagine you're standing on a train platform. A train goes zooming past you, moving really fast. Right as the middle of the train passes you, two lightning bolts strike, one at the front of the train, one at the back. The light from both lightning strikes reaches you at exactly the same moment. You conclude those lightning strikes were simultaneous. They happened at the same time. Makes sense, right? The light from both reached you at the same time. You're standing right in the middle, so they must have happened at the same time. But now let's think about someone riding in the exact middle of that train. From their perspective, they're moving toward the front lightning strike and away from the back lightning strike, which means the light from the front lightning strike reaches them first. Then, a moment later, the light from the back lightning strike reaches them. They conclude the front lightning strike happened first. Then the back one happened. Now, in classical physics, we'd say, well, that's just an illusion. The light reaches the person on the train at different times because they're moving, but the lightning strikes were still simultaneous. There's an absolute truth about when they happen. But here's where Einstein blew everyone's mind. There is no absolute truth about when they happen. If the speed of light is the same for everyone, if it's absolute, then we can't dismiss what the person on the train observed. From their reference frame, truly and genuinely, the front lightning strike happened before the back one. Both observers are right. There's no privileged perspective, no true order of events. This is the relativity of simultaneity. Events that are simultaneous for one observer are not simultaneous for another observer moving relative to them. Your brain is screaming, but that's impossible. Either the lightning strikes happened at the same time or they didn't. That's basic logic. And Einstein says, nope, there is no universal. At the same time, simultaneity is relative. It depends on your motion. This is where physics breaks. This is where everything you thought you knew about time shatters into pieces. See, we've always thought of time as this universal thing, a cosmic clock ticking away, the same for everyone everywhere. Newton imagined absolute time, a single timeline that all events exist on, flowing uniformly, independent of anything else. But if simultaneity is relative, if two observers can disagree about whether events happened at the same time, then there's no universal now. Your now and my now are different if we're moving relative to each other. We're not living in the same moment. We're not synchronized. Time is personal. And if time is personal, if it depends on your motion, then time must be flexible. It must be able to flow at different rates. Here's where it gets even wilder. Let's say you're on that train and you've got a clock. From your perspective on the train, the clock ticks normally, 1 second per second, as it should. But I'm standing on the platform, watching you zoom by. I look at your clock through the train window, and here's what I see. Your clock is ticking slowly, not because it's broken, not because of some mechanical issue, but because time itself in your reference frame is running slower than in mine. From my perspective, your time has slowed down. This is called time dilation, and it's real, not an illusion, not a trick, actual, genuine, measurable time dilation. Atomic clocks flown on airplanes run slower than atomic clocks left on the ground. Particles moving at high speeds in particle accelerators live longer than particles at rest. GPS satellites have to account for time dilation, or they give you the wrong location within minutes. This is reality. Time is not absolute. Time is flexible. Time depends on how fast you're moving. But wait, there's more. If time can stretch and compress, then space must do the same, because space and time are connected. They're not separate things. They're a unified fabric, space-time. So when you're on that train, moving at high speed, from my perspective, watching from the platform, you're not just experiencing time slower, you're also physically contracted in the direction of motion. The train is shorter, you're thinner. Everything is compressed. This is called length contraction. And again, it's real. Of course, from your perspective on the train, everything seems normal. Your rulers measure normal length. Your clocks tick at normal rates. It's only when we compare notes between different reference frames that we see these effects. And here's the absolutely crucial point. None of this is because light has some magical property. Light isn't doing anything special. Light is just revealing to us the true nature of space-time. The speed of light is constant because the speed of light is the conversion factor between space and time. It's the cosmic speed limit, the maximum rate at which causality can propagate. It's built into the very structure of reality. Einstein realized there's no absolute space, no absolute time, no absolute motion. There's just space-time and the relationships between events in space-time and the speed of light as the one absolute speed connecting it all together. Every observer is equally valid. There's no privileged reference frame, no objective view from nowhere, just different perspectives on the same unified space-time. This is special relativity, and it comes entirely from taking seriously the idea that the speed of light is the same for everyone. So what does all this mean? What are the consequences of this revelation? Well, first, there's no universal now. When you look at a distant star, you're seeing it as it was years ago. But there's no objective answer to the question, what is that star doing right now? Because now depends on your reference frame. 2, time travel to the future is possible. Not science fiction, actual time travel. If you get in a spaceship and accelerate to near the speed of light, then return to Earth, you will have aged less than people who stayed behind. You will have traveled to their future. This isn't speculation. It's a direct consequence of time dilation. In fact, astronauts on the International Space Station age slightly slower than people on Earth, only by milliseconds, but it's measurable. 3, mass and energy are equivalent. This comes from pushing special relativity further. If you do the math, if you work through what happens to mass as it approaches the speed of light, you discover that mass increases. And if you keep pushing the equations, you get the most famous equation in physics, E equals mc squared. Energy equals mass times the speed of light squared. Matter is frozen energy. Energy is liberated matter. There are two forms of the same thing. This equation explains nuclear power, nuclear weapons, the energy of stars. The sun is converting mass into energy every single second, and that's why it shines. 4. And this is just special relativity. When Einstein added acceleration and gravity into the mix, things got even stranger. General relativity revealed that massive objects bend space-time itself. Gravity isn't a force pulling things together. It's objects following curved paths through curved space-time. Black holes become real. The universe itself becomes dynamic, expanding, evolving. All of these mind-bending revelations came from Einstein taking seriously what the experiments were showing. That light doesn't care how fast you're moving, that the speed of light is absolute, and it all started with a teenager imagining riding alongside a light beam. So why was Einstein the one who saw this? Why not Newton, Maxwell, or any of the other brilliant physicists working on these problems? I think it's because Einstein was willing to follow his imagination to impossible places. He was willing to question everything, even things that seemed obviously true, like absolute time and absolute space. He didn't dismiss his teenage thought experiment as silly. He took it seriously. He sat with the paradox for years until he found the answer. And the answer was that the universe is far stranger than we imagine, that reality doesn't conform to our intuition, that space and time are flexible, relative, interconnected. But here's what I love most about this story. Einstein didn't need a laboratory. He needed imagination, the courage to ask, what if, and follow the logic to the end, even when it seemed absurd. That's the power of thought experiments. That's the power of asking simple questions and refusing to accept easy answers. The universe is weird, gloriously, beautifully, impossibly weird. And all you need to see it is the courage to imagine what would you see if you chased a beam of light. Now you know.